Assalamualaikum warahmatullahi wabarakatuh and good days. My name is Irfan bin Ahmad Zafi. I'm a student from Faculty of Mechanical and Automotive Engineering Technology FTKMA from the UMPSA. Today I would like to present about Battery Thermal Management System BTMS, a comprehensive system review of fundamentals and challenge. Okay, let's start with BTMS. It is a hardware-software framework essential for maintaining lithium-ion battery within their ideal operation temperature range. To prevent degradation, these batteries must stay below 50 degrees Celsius. The requirements for BTMS change depends on how the vehicle being used. During charging, the vehicle must provide efficient heat dissipation to handle rapid heat generation for electrochemical reaction. During discharging, especially under high acceleration, the BTMS must provide a rapid cooling response to manage thermal spike and prevent hotspot. Even when idling, the system must maintain thermal stability against ambient environmental conditions. Ultimately, the BTMS serves three primary objectives. Longevity, it minimizes degradation by reducing side reaction like SEI group. For performance, it ensures consistent power delivery by maintaining stable electrochemical kinetics. For safety, it limits temperature rise to prevent failure and enhance overall system reliability. Okay, next is the critical need for thermal control in BTMS. The technical needs for this is critical because lithium-ion batteries are highly sensitive. High temperature accelerate capacity fade, while uncontrolled exothermic reaction can lead to thermal runaway, resulting in fire or explosion. We also cannot ignore the impact of cold climates, which increase internal resistance and slow down lithium-ion diffusion, leading to a reduced capacity. Our engineer objective is to maintain an optimal range of 20 degrees to 50 degrees Celsius to minimize thermal stress over the battery's lifespan. A major challenge is thermal non-uniformity. Uneven heat distribution leads to cell imbalance and uneven aging. To keep a battery pack efficient, we must achieve a uniform temperature distribution where the difference across cell or Tmax is less than 5 degrees Celsius. Okay, next is key finding from recent literature from 2022 to 2024 for cooling techniques. It shows significant progress. For example, Chen from 2023 demonstrated that parallel channel design reduced maximum temperatures, though they increased parasitic power consumption. In liquid cooling, Al-Kobayashi from 2022 identified the M-hexane as a promising lightweight dielectric coolant. For phase change materials (PCMs), research by Shi from 2023 shows that the internal PCM integration can improve thermal uniformity by 50%. Most impressively, Ahmad from 2022 proved that PCM liquid hybrid system can maintain temperature gradient below 0.7 degrees Celsius. Okay, let's look closer at the types of BTMS. Air cooling can be passive or active. It is favored for being low cost and lightweight, but it suffers from poor temperature uniformity and is generally not suitable for high performance EV. Liquid cooling uses coolant like water glycol mixture. It offers superior heat transfer and enables compact design, but it is more complex and carries a leakage risk that could lead to a short circuit on high voltage environment. As you can see from this picture, this is a basic liquid cooling system for EVs. Phase change materials (PCM) are fascinating because they are passive. They absorb latent heat during melting to provide nearly constant temperature control. However, standard PCM has low thermal conductivity and can experience volume expansion that stresses the battery modules. As you can see in this picture, the battery cells is inside this box and it's covered by the BTMS inside the battery casing. This led us to a hybrid system, which combined heat methods like liquid plus PCM. Here, liquid cooling handles steady state loads, while the PCM absorbs transient peak spike. This is the most efficient solution for high performance EVs. achieving gradients below 1 degree Celsius. As you can see in this picture, this is a basic heat pipe cooling system method. Despite this technology, we still faces the hotspot problem. Non-uniform airflow or cooling distribution leads to localized overheating, which accelerates cell degradation and reduces the usable capacity of the entire pack. For the engineering and weight, we also face energy and weight bottlenecks. High-performance pump and fan created a parasitic load that reduced the driving range, and liquid cooling architecture adds significant mass to a vehicle. For safety risks, liquid cooling system introduce leaking hazard. For material limitation, PCM experience volume expansion contraction during phase transition, which can induce mechanical stress on material modules. Cost barrier, advanced BTMS solutions like hybrid system or nanotech enhanced PCM involves high material and manufacturing costs. And this increases both system cost and design complexity. To summarize our problem statement, we have a uniformity gap in air system, energy efficiency due to a lack adaptive control, and materials limitation in standard PCMs. In conclusion, the hybrid advantage, integrated liquid and PCM is currently the most effective solution for high-performance EV. Looking forward, the next generation of smart BTMS will integrated AI-driven thermal control and advanced sensor network. This allows the system to adapt in real time based on battery state of health and driving condition. Thermal management is a critical enabler for EV safety, charging speed, and lifespan. Solving this challenge is key to widespread EV adoption. That's all from me. Thank you.